So when we do alkene reactions, we have to do all of these reactions. There are 2 pages. Okay, so it's actually a lot of reactions. I will see how much I can get through, for your exam, because your exam is definitely chapter 7, which itself is pretty big chapter. But I don't think I will be able to finish alkene reaction. So we'll see how far we get. And that's all that will be on the exam then. Okay, so not everything is going to be on there. So this one is at the end of your books, of your manuals. Okay, so you have a periodic table, hopefully, and you have the pKa chart and all that. You have alkene reactions. You should have another one for alkyne reactions also. Okay, but we're going to start with this one, and I may not do it exactly in this order, but these are all the reactions that we have to do. So alkene reactions are going to be now all addition reactions, okay? And you can see that even here, that in the starting material, you have an alkene, but in the product, that alkene is gone, okay? It's not there anymore. So the product is then saturated, as we say, okay? So it does not have any more unsaturation anymore. So this chart is actually very good, okay? So I will explain more later once we start actually doing the reactions. So let me open my document really quick, and I don't see that here. Hold on. It's probably because I found it. Okay, so alkene reactions. What we did just now was all alkene synthesis, how to make an alkene. And now we're talking about what to do with those alkenes. And these reactions, oh my God, they're really good reactions. And they're also very common reactions, okay, to do in any lab. So let me just take a random alkene, something like this. And let me take a random compound that you're adding on. XY. So what happens in this case is when you add something, it's going to add in a 1-2 addition. When we were doing the elimination, I mentioned to you that we do a 1-2 or an alpha beta elimination. So now when we're doing the addition, it is the same thing. Okay, it's a 1-2 addition because the double bond is on 2 carbons. Okay, and so you're going to add on both the carbons, okay, not just 1 carbon. So we'll start with the first reaction, okay, that I want to talk about, which is hydrohalogenation. The thing is about these reactions that is really good is that once you understand one of them, the rest of them will be a lot easier. So hydrohalogenation. So hydro and then a halogen is X. Okay, X meaning fluorine, chlorine, bromine, iodine. And again, we don't usually work with fluorine, so it's either HCl, HBr, or HI. Okay, so let's go ahead and write the mechanism for this. I hope you're also getting comfortable writing things on the arrows, okay, because you can see we use arrows a lot. So when you look at this starting material and the reagent that we have, I hope there are some things going on in your mind, okay? And the thing that going on mainly should be, where am I going to start my arrow from? Okay, because when you're writing a mechanism, then you have to know where to start your arrow from and where are you going to end it, which means that the first thing you need to do is classify everything as a nucleophile, as an electrophile. Now, HCl, you know, is an acid. So if this is an acid, this must be a base. Now, this base, you don't see hydroxide. So obviously, this is going to be a Lewis base. Okay, so it's not your traditional base where you have hydroxides. Okay, so if this is the base, then this is obviously the nucleophile, and then acid is the electrophile. So once we've clarified all of these things, then we can start our arrow, because Arrow starts from the nucleophile, goes to the electrophile. What is my electrophile? Electrophile is the H, not the Cl, because the Cl is going to be minus. So what happens there? Once you pick up a proton, now you have two choices. Okay, you have carbon number 1, carbon number 2, and this is not about nomenclature. Okay, this is just about the double bond. So you have carbon number 1, carbon number 2. Where are you going to place that hydrogen? And honestly speaking, right now at this point, it doesn't matter. You have to pick one. The other one gets the carbocation. Once you have that, then the next thing is, now this is the electrophile and this is the nucleophile. So now the chloride is going to attack the carbocation. And here is your XY. The two things. Now you don't have to draw the hydrogen, right? So which means that your product really is this. And since it's a single bond, you can write the chlorine anywhere. So everything is rotating, no problem. So that's a 1-2 addition. Now, if things were so easy, life would be fine, but things are not all that easy all the time. So what's going on? Okay, and reduce that a little bit. And so this alkene that I took right now is what we call a symmetrical alkene. It's an internal alkene, yes, but it's also a symmetrical alkene, all right? Now what I'm going to do is I'm going to take an alkene that is not symmetrical. This is an asymmetric alkene because the groups on either side of the double bond are not the same, right? They're not equivalent. One has 2 methyl groups, on the other side there's only 1. But that's not the point. The point is that there are different groups, okay, on either side. So one of them actually has hydrogen. So now if you have HCl, and now you draw this arrow. If you don't draw the second one for Cl, it's fine, okay? Some arrows I can live without. But if you want to, you can go ahead and do that. But if you don't draw, it's not a big deal. So now when you do this, now where does the hydrogen go? Okay, so now you have 2 places. I'm going to draw both of them, okay? And then I know I'm sure you can also decide where it's going to go, but I just want to go ahead and do this anyway. Remember, there is a hydrogen here. So even though we're not writing it out, there's actually a hydrogen here. This hydrogen is this one. So I would like someone from the class to tell me which carbocation is more stable, the first one or the second one?
Is it the second one?
Is it the second one or it is the second one?
It is.
It is. Very good. Thank you so much. Yes, it is the second one because that is tertiary carbocation. You're absolutely right. So what's going to happen? This is going to form. The first one does not form. Okay. So then it changes everything, right? It'll change your product. So now take chloride comes in. There we go. And there is the chloride. And you can draw the hydrogen here if you want to, but essentially, no, not really. You will see that I have some mechanisms in this chapter, and I don't do all the mechanisms. Okay, and I will tell you which mechanisms I follow because you can't do all the mechanisms. It's not possible. Okay, so this mechanism, yes, you have to do because you're forming a carbocation. Okay. Okay, so how are we going to write this? Okay, let me just show you. If I were to ask you this without the mechanism, okay, then here is what you will do. Okay, because this is what I'll give you. I never write hydrogen, right? So you have HCl over here. This is it. That's what you will write. No hydrogens necessary, okay? This is the main reaction that's going on. Okay, so once you have this, now I need to talk about something else, okay? And again, I'm going to bring up this word, regioselectivity. Now regioselectivity is a little bit different. Before, regioselectivity was Zaitsev's product and Hoffman product. Now regioselectivity is just a little bit different, okay? So I'm going to go ahead and write this again because I need to make sure you understand this, okay, what's going on. So if you take this and you add HCl to this, okay, and let me write both the products. So let's say you get Cl here and you have H here, okay? And then the other product would be if you were to get H here and Cl here, right? Just I'm reversing where things are adding. So this one, the first one that I have here, this is also the one that you got, okay, because of the carbocation. This is called Markovnikov product. That's the regioselectivity we're talking about now. And again, as I said, if you don't remember the word regioselectivity, I don't care. I need you to remember Markovnikov product. So what is Markovnikov product? Markovnikov product is when hydrogen goes to the carbon with more hydrogen. Hydrogen adds to the carbon with more hydrogen. So this carbon has more hydrogen, and that is where your hydrogen is adding. Let me take a different color. So this carbon is the one that has more hydrogen. So this hydrogen is already there, but this hydrogen, the other one, you're adding now. Okay, so this hydrogen and this Cl is being added. So what is the other product then? Sadly, it is the anti-Markovnikov. There's no other name for it. So anti-Markovnikov. Some people write like KOFF. Depends. I don't know what the deal is. Markovnikov, I write it as a V, and I think Klein does too. So you don't have two products, by the way. We don't have two products. Markovnikov product is the only one you get. This is the only product. Oh, why only product? In this case, the only product, by the way. Okay, not all the time, but in this case, this is the only product you will get. And that's the Markovnikov product, which means now you have to watch out, okay? It's not just as simple as adding something. So let me write another one so you kind of understand, because, everything is kind of like this. And I'll choose the blue pen. I don't know if the black one is bothering you. It's bothering me a little bit. I think a blue pen is a little bit gentler. So if you have something like this, and I ask you to write, okay, what is the product I'm going to get? So here, this is it. This is the only product you will get. So I did the mechanism first. Okay, I did not give you the product first. I actually wrote the mechanism first. But actually, when Markovnikov did his work, he did not have the mechanism. Okay, so when he did this work, he only found out that, oh, the hydrogen is going to the carbon with more hydrogen. At that time, he did not know what mechanisms were, and nobody had done any work on that. So after the mechanisms were worked out, it turns out it's all about the carbocation. So the more stable carbocation will give you the product. Okay, so that's the mechanism that is being followed. What does it mean? It means that the mechanism we are following is a carbocation mechanism. Okay, and let me give you my disclaimer right now, is anywhere that we will have a carbocation, I will be writing the mechanism. Okay, for that. Some of the other mechanisms I don't follow so much, but whenever there is a carbocation, I will do the mechanism, because carbocations give us different kinds of products. Okay, and it'll be easier for you also. Okay, you'll see that you kind of start getting used to the mechanisms. Okay, and so that is the first reaction, which is hydrohalogenation. Okay, so HCl or HBr, something like that. Any question about this one? If you have a symmetric alkene, by the way, then this doesn't work. Okay, I mean, like, not that it doesn't work, it's just that you don't have a Markovnikov product. Okay, so the first alkene that I wrote out, the first alkene that I wrote out doesn't even have any Markovnikov product, okay, which is this one. This is not Markovnikov or anti-Markovnikov because it's a symmetrical alkene. Markovnikov product is from only when you have an asymmetric alkene, okay? And I give you both kind of reactions, okay? Usually I give you asymmetric alkene because the whole purpose of this reaction is to learn that you will get a very specific kind of product, okay? So, and if you're thinking, and I don't know if you're thinking this or not, well, I don't want the Markovnikov product, I want the anti-Markovnikov. For that, you'll have to wait, okay, a little bit, because yeah, I will cover that too later. Okay, so the second reaction that I want to talk about, I will not do this one yet. I'll talk about halogenation. Halogenation is X2, which means you're adding Br2, Cl2, anything like that. Okay, so that is halogenation. So in this case, if you take an alkene and you add a halogen, now here I'm going to also add the solvent. This is what we do in organic chemistry. At least I do this. I'm not going to say everybody does that. And you have to watch out for this. Okay. So you will see that, even in okay, let me finish this one first. So what we do is we write the reagent on the top. I do that. And I write the solvent at the bottom of the arrow. Okay. But you can write like this also, comma, CCl4. And you just have to know that CCl4 is the solvent. Okay, so CCl4 is not there for any reaction. Okay, it's not a reagent. So you have to kind of know this. I write it on top of the arrow and bottom of the arrow, so that way you at least have a little bit of an idea what to focus on, but it's not all the time though. Okay, so be careful with this. And learn to recognize what is the reagent, okay? What is the one that is actually doing the reaction? So here, when we do this reaction, this is what we end up getting. It's important that you write the stereochemistry as I'm writing it. And you also get the enantiomer, plus enantiomer. So you have the bromides going in the other directions. And what this is a trans relationship. So you never get a cis. So what is happening here? So to understand why we're getting trans, you have to know the mechanism a little bit. So here I will explain just a little bit of the mechanism. This one you don't have to memorize if you don't want to, that's fine. Okay, because it's important to know what kind of product you're forming, but not so much of the mechanism. Okay, so here what happens is that you have the bromine. Let me erase this 1 second. So I could show this. So here's bromine. The double bond is picking up the bromine, which is a really, really weird because the bromine-bromine bond is not a polar bond. So if it is not a polar bond, then why is it breaking like that? Well, that is just the energetics of the reaction. That's how it works. So in this case, what happens is the alkene picks up a bromine. Once it picks up a bromine, this is what you end up getting. This is called a bromonium ion. Just like we called the oxygen one an oxonium ion, that was a positive. This one is a bromonium ion, Br positive. Just one last step. Because now the second Br is going to come in. And now imagine having a cyclic compound where you have a three-membered ring sticking out of it. Okay, so you're going to have a little bit of steric hindrance. Okay, and so because of that steric hindrance, the bromide that is coming in is going to have a backside attack. So which means that, I mean, it's very hard for me to draw it, but it is coming from behind, and then this will open up. So if it is a backside attack, it means that one bromine is going to be in the front and the other one is going to be at the back. That's really what it is meaning. This kind of a product, this kind of an addition is called an anti-addition. Anti meaning when the groups are adding on opposite sides. That's an anti-addition. You will see that in the chart that I just showed you. I have given you all of these things in that chart. Okay, so that way you have everything together. You should make your own if you want to. So this one here, you can add chlorine, you can add bromine. Okay, don't add iodine or fluorine. Don't do that. Okay, because those work a little differently. Any questions? I just want to specify one more thing before I move on from halogenation, is that when you're writing the products for me, you have to show the stereochemistry. Okay, I said that for substitution reactions also, and I'll say it here also. Okay, in substitution reactions, you had to show me the inversion of the stereochemistry, or if you have a racemic mixture, you have to show that. Here also you have to show this, okay? Because this is a characteristic of the reaction, and I need to make sure that you know that this is a characteristic of the reaction. So that's halogenation, that's it, okay? Small reaction. So now we'll go on to, it's halohydration, okay? So we're doing two things here together. This is the last reaction I'm going to do today. The one reaction that I wanted to do is way too long, so I'm going to wait for next week to do that. I don't want to do it today. So halohydration is when you are adding a halogen and you're adding water with it. So in this case, I'll take the same one for now, just so that I can give you an example. So here you have chlorine and you also have water. You will still form anti. So this is also anti-addition. Okay, how does this work? Similarly, as it did to the other one. So which means that here you're going to attack this, get the chloronium ion. It could be bromine also. But this one is just one more step, okay? So two more steps, I should say. And then water will come in. So this will be the backside attack. This opens up. It doesn't matter what you write in the front and what you write at the back. It's just that it should be anti. That's all. That's what's important. I probably will not be asking you to write the mechanism for this one. So it's not such a huge deal, but it's still a good idea to write the mechanism. So now water will come in and deprotonate this, and that will give you the alcohol. Let me go ahead and change this so that you don't feel like, what did I do? What did I just do? So here, I'll just switch this around. So OH is at the top and then Cl is here. So that's halohydration. But there is an issue, a small issue, not a huge issue. So in this case also, we're going to have some regioselectivity problems. What is that? So let's say you have an alkene like this. And you're doing this. So let me just draw the skeleton first, okay? The double bond is going to go away. So now the question is, I'm going to have to add the chlorine, and I'm going to have to add an alcohol, an OH group. So where am I adding it, right? Because this is 1, this is 2, this is 1, this is 2. So where am I adding what, right? So can the chlorine go on 2 or the alcohol goes on 2? So this has to do with how the attacking is happening. And if you look at the mechanism, the way this works is that the water is attacking the backside. Okay, so the way we look at this reaction is actually a little bit more in the sort of SN1 mechanism. So when you think of it in terms of SN1 mechanism, then you have to think about a stable carbocation. So then when you look at that, carbon number 1 versus carbon number 2, carbon number 1 gives you the more stable carbocation. So that is where you're going to get the alcohol. That's how it works. And let me erase the 1 and 2 so that way I can show the stereochemistry also. And this is not a chiral center by any means. Okay, it's not, because you got the 2 methyl groups there, and this one is the chiral center, but the other one is not. The other way to look at this is it's also the Markovnikov addition. The only thing here about Markovnikov's addition is that halogen goes to carbon with more hydrogen. So instead of hydrogen going to the carbon with more hydrogen, it is actually the halogen. Hopefully it will be easier to remember when you say it like that. You know, when you come to this part of organic chemistry, there's a lot of memorization to do. But there's a lot of understanding also. I mean, the understanding is still there, okay, that you understand the concepts. And that's why I try to do the mechanisms, so it will help you. But you have to memorize also a lot of these things, okay? With the SN1, SN2, that's a lot of concepts, okay? There's not much you can memorize. But here you have to memorize a little bit, okay? So one thing I want to just add on here, because I know you have the lab for alkenes coming up. So I'm going to write that here for the halogenation because otherwise you will say, oh my God, she didn't mention this. This here is actually the halogenation is actually a qualitative test. Okay, so let me write that for you over here. This is a qualitative test. Qualitative. What does a qualitative test mean? Qualitative test means that if you want to check if a sample is an alkene or not, then this is a reaction you do. Okay, so how does it work? When you have an alkene and you add bromine to it, bromine is actually a brown liquid. Not brown, kind of reddish, actually. So it's a reddish liquid, but once you add it to the alkene, it will add on to the alkene, right? Because it's an addition reaction. So the brown color disappears. Okay, that's kind of what happens. And you will do this in the lab. All right. So when you are synthesizing the alkene, I think you all have the dehydration of an alcohol as your lab. Okay, so in the qual test, the bromine decolorizes. Here, I'll just write that over here. And bromine, as I said, is a red colored liquid. And so that is how you know it's a positive. So if you don't have an alkene, the solution should stay red. Okay, but if you have an alkene, then it should go colorless, all right, from there. So this is a good start for us to do for alkene addition reactions because I've covered a lot even in this one. So there's the Markovnikov product, and then we also have done the anti-addition, okay, over here, and qualitative test. Oh my God, so much so, okay. So let me stop the share.